Hello everyone, welcome to the video lecture series of the subject code KEC 053 with the subject name VLSI technology as per AKGEC syllabus scheme. In the previous class, we have started the chemical etching, that what is the need of chemical etching and what are the types of etching processes, how the isotropic and anisotropic etching works, and we have covered the wet chemical etching in the previous class, right? Now in this section we are going to cover, this is the 17th lecture, and we are going to cover the dry chemical etching technique. So in the previous class we have seen that in case of wet chemical etching, your etchant solution should be in the liquid form, right? The first requirement is your etching solution should be in the liquid form. The second requirement is we should have a continuous flow of etchant solution so that the concentration gradient will remain same throughout the solution. We should stir it properly, and the residual product should be taken out time to time, continuously taken out so that your reaction products, so that your reaction etching reaction can be taken can be in continuous process. So today we are going to cover the dry etching process. Some of the dry etching process are plasma etching, gas etching, physical dry etching, chemical dry etching, physical chemical etching. So as per the definition, in case of dry etching, plasma or etchant gases are used to remove the substrate material. The reaction that takes place can be done utilizing a high kinetic energy of particle beam, chemical reactions, or the combinations of both. Okay, so here in case of dry etching, your requirement is your etchant solution should be in the gaseous form, right? So it should not be in the liquid form, it will be in gaseous form. So that is why it is known as dry etching. So in case of physical dry etching, the physical dry etching requires a very high kinetic energy of ion, electron or photon beam to etch off the substrate atoms. So when the high energy particles knock out the atoms from the substrate surface, the material evaporates after leaving the substrate, and there is no chemical reaction. No chemical reaction will take place. Only the layer which is unmasked, it will be removed only. So the physical reaction which takes place here, we can see that this purple circles are for the plasma, and here we have the silicon atoms, right? So here we have the mask, and we have to remove the silicon dioxide from the here only, right? We have this silicon atoms. So when this plasma strikes over there, some of the silicon atoms, it will be evaporated off from the surface. We can see that they are evaporating, right? So they are evaporating from the surface when your plasma atoms are reacting with this surface. So in case of chemical dry etching, that is the case of physical dry etch. In case of chemical dry etch, it is also known as vapor phase etching, and it does not need any liquid or chemical etchant. This process involves a chemical reaction between the etchant gases to attack the silicon surface, where we have to remove the silicon dioxide layer, right? The chemical dry etching process is usually a isotropic process which exhibits a very high selectivity. Over a selective area, we are going to etch with the help of this chemical dry etching process. So the selectivity will be very much high. An isotropic dry etch has the ability to etch with a finer resolution and higher aspect ratio as compared to your isotropic etching, and due to the directional nature of this dry etching, undercutting can be avoided. Undercutting means whereas in case of wet etching, isotropic etching, suppose this is the mask. Okay, this is the mask. Your etching, we know that your etching will be something like this. Undercutting is also there, right? So this undercutting will be avoided with the help of this chemical dry etching. So some of the ions that are used in chemical dry etching are tetra, tetrafluoromethane, that is named as CH4, sulfur hexafluoride SF6, nitrogen trifluoride NF3, chlorine gas and fluorine gas. Okay, so these are the some chemicals that are used in the chemical dry etching. So we have the same diagram. We have this some reactive ions which will react with this reactive ions. It can be CH4, okay, it can be SF6, okay, it can be Cl2, it can be NF6, NF3, it can be fluorine gas. Okay, so any of the reactive ions can be used. They will react with the silicon, and the silicon will get evaporated from here, and here we can see that no undercutting is there, and we have a very sharp etching under this area. So next, the next etching process that comes under dry etching technique is the reactive ion etching. Reactive ion etching, it is also famous as RIE. So in this reactive ion etching, both physical and chemical mechanism are used to achieve a very high level of resolution. The process is one of the most diverse and the most widely used process in the silicon industry. And latest research is also going on how this RIE etching, reactive ion etching, can be used to etch the different type of material. For different type of material, obviously this reactive ion etching is going to give you some different results. So this is one of the upcoming research areas in this technology. So since this process combines both physical and chemical interaction, the process is much more faster, and high energy collision from the ionization helps to dislocate the etchant molecules into more reactive phase. So here we can see the we can see the diagrams of the furnace which we are going to use for the etching in case of dry etching. So this is the simple dry etching technique. Here we have the chamber. Some RF heater will be there which is used to heat up this wafers, heat up this electrode. Some wafers are placed over this electrode, okay, over this cathode. Etching gas will be passed from this side in the chamber. This is named as ground shield, and extra gases will be taken out from there, right? So what we are going to do here in this reactive ion etching, which a very much similar operator here is the noble gas plasma is replaced by the molecular gas plasma, which is similar to the plasma etching. So under the appropriate condition, both RIE and the plasma etching can give these both techniques will give you a very high selectivity and a high degree of anisotropy. Okay, so in the second diagram we can see that we have the plasma which is created between these two electrodes. Okay, we have this gas ring. The pumping system will be there. This complete system is known as Pyrex cylinder. Wafers will be placed over this ground electrode, first lower electrodes, where the wafers are placed. Here the wafers are placed, and RF signal will be applied to this upper electrode. Okay, so gases will be applied from here, from this side, and they will be pumped out from this side. Okay, so in this diagram we have seen that a parallel plate plasma etching system. The plasma is confined between two closely spaced electrodes. Molecular gases containing one or more halogen atoms are fed through the gas ring. The typical operating pressure here, it is very much relatively high, that is 0.1 to 10 torr. So this is the process of reactive ion etching, where your cations are produced from the reactive gases, which are accelerated with the energy and they are accelerated towards the substrate, and they will chemically react with the silicon. And the typical typical gases which are used for the silicon in this reactive ion etching process, they are CF4, SF6, BC12, BC12, write it at BC12 plus Cl2, chlorine gas. Okay, so here we can see that we have some plasma is there, reactive ions are there, and they are going to react with the silicon, and as a result some of the silicon will be evaporated, and we are going to have a very high degree of selectivity and a very sharp edges which are going to be etched with the help of this reactive ion etching. Next is the plasma excitation and the plasma surface interaction. The plasma is fully or partially ionized gas which contains ion, electrons and neutrals. Okay, the plasma in most of the VLSI process is a very weakly ionized plasma. It is known as glow discharge. It contains a significant density of neutral particles, that is 90% in 90% of the etchant solution. They generally contain the glow discharge, and although this plasma is neutral in a microscopic sense, it behaves quite differently from the molecular gases because it contains a charged particles that can be influenced by the electric or magnetic field. So plasma is produced when the electric field is applied across the two electrodes between a gas is confined at a very low pressure. It causes the gas to break down and to become ionized. So here you can see that between these two electrodes, some gas will be confined at a very low temperature. It is known as the cathode shield and anode shield. Here it is known as the chamber, and we ionize this gas at a very low pressure, and we can see some glow, green color or any specific color discharge that is known as plasma glow reaction. So, a simple DC current power can be used to generate the plasma. Okay. So, a simple DC current power can be used to generate the plasma, but insulating material requires the AC, whereas the insulating material requires the AC power to reduce the charging. In case of plasma etching, your RF frequency is used to generate the gas discharge. One reason for doing is that the electrodes do not have to be made of a conducting material, and the another reason for using this plasma is that your electrons can pick up sufficient energy during the field oscillation to cause more ionization by the electron neutral atoms collision. So, with the help of this plasma, your electrons will get very much easily ionized, and they will pick up very high speed, and it will react with the silicon atoms, and we are going to have the resultant. So, as a result, the plasma can be generated at a very lower pressure, that is your 10 raised to the power -3 torr. So, this is the schematic view of the microscopic process that occurs during the plasma etching of the silicon wafer. So, it is very much important to understand. Here we have the silicon wafer. Okay. So, from here this complete is the chamber, it is inside the chamber. So, from first step here, when we pass the gases, the incoming gases, the electron impact will be there, the gas will be fragmented and it will be transported, and in the gas phase reaction it will be directed towards the substrate, and here it will be absorbed. It will absorb some of the reactants, and then some reactions will be carried out, whether some electrons will leave their places or some impurities will take the places, right. So, some intermediate reactions will be there. So, as a result, we are some absorbed product will be there. These gaseous products we have to take out these products. So, this is known as desorption. So, we have to take out these gaseous products and transport them into a bulk of gases, and then again this process is repeated. Okay. So, this way extra gases will be pump out from this side. Okay. So, this way we are going to have the plasma etching. So in this lecture we have covered the dry etching techniques, that what are the techniques which comes under dry etching. We have seen the vapor phase etching technique, right, chemical etching technique, plasma etching technique, and the reactive ion technique. So depending upon your application, what degree of uniformity we need to etch, depending upon that we can have the we can select any of the etching process. So but generally reactive ion etching, and plasma etching is used in most of the etching process. Okay, so till now we have covered, we have the silicon dioxide here. From here we have removed the silicon dioxide. Okay, so we have created a window here. Now in the next upcoming lecture we are going to diffuse some dopants depending upon our requirement. We are going to diffuse some elements in this. So that process is known as diffusion. So in the upcoming lectures we are going to learn about diffusion and ion implantation process. With the help of this ion and implantation process, we are going to have some N plus or P plus diffusions, right? So thank you so much for today's lecture. Some more graphs are there in this, we can include here, that lateral etch rate and the lateral etch rate and the vertical etch rate we can indicate with the help of graphs. So here we can see that when positive ions react with the surface, we are going to have the vertically they will move more inside, and we have the more etch rate, right? Laterally, in the lateral direction we have less etching, so the lateral etch rate is slightly less, right? So similarly, the flow rate of the molecules will be indicated. And lastly, when your gas is mixed with one or more additive gases, both the etch rate and the selectivity can be altered. So here in the diagram we can see that silicon dioxide, it is at this level, right? Polysilicon, it is degraded to 50, right? So similarly we have this another polysilicon which is mixed by some gases. Okay, so this etching rate of silicon dioxide is approximately constant, and in addition to that 40%, if you add 40% of hydrogen, the etch rate will be dropped, and depending upon the gases which we are going to add as a etching solution, as a etching gases, so depending upon that your etch rate will be different. So lastly, the opposite effect can be observed by varying the gas composition of sulfur, hexafluoride, SF6 and chlorine, and the etching rate of silicon can be adjusted to 10 to 80 times faster than that of silicon dioxide. Okay, so this is the case of your this is the case of your silicon, and we have the case of your silicon dioxide. In both the cases we have the different etching rate. Okay, so these etching rates can be varied from 10 to 80% depending upon the gas composition, which type of composition we are using. So thank you so much for this lecture. In the next lecture we are going to learn about the diffusion process, that how we are going to diffuse the dopant elements, how the ion implantation is done, what basically is the difference between the two processes. Thank you so much.